1 for ee186. First lecture is regarding to the lab on spectrum analyzer basics. And just to give a preface to the course in general, we're going to be using a couple pieces of test equipment consistently throughout the semester, and one of the main ones is the spectrum analyzer. So we're going to start off just doing a few key measurements and playing around with some of the settings on it and seeing what the spectrum analyzer can actually do for us. In addition to these notes, online on WebCT you'll find the Agilent Application Note 150. It's a 64-page document, so you may not want to print it out, but there is a hard copy also in the lab. So, but I would suggest that if you have any questions, in addition to what we're going to talk about here about what a spectrum analyzer can do, look there. In addition, there is the user manual for both spectrum analyzers we have, namely the vector signal analyzer, which is the HP 89441A. Very nice piece of equipment that we'll really start using the high-end features of later on in the semester, and a portable spectrum analyzer, this Ritsu units MS2711B. In talking to people that are working out in the field, this seems to be a very popular unit. It's one of really the first portable battery-powered spectrum analyzer that goes up to 3 gigahertz that hit the market, and I think it really has sold quite well. There are some new devices that are coming out, but I think this is kind of one that you will see quite a bit in the field. Okay, so before we get into what a spectrum analyzer does, we first of all need to talk about the units of measurements that we'll be using. Due to the large range of power levels that we experience in a communication system, anywhere from milliwatts or sub-milliwatt ranges for signals propagating inside a circuit to hundreds and thousands and maybe hundreds of thousands of watts being broadcasted out of a, say, FM radio station tower, or hundreds of watts coming from a satellite downlink. There's a huge range of power levels that we're going to be dealing with. So as such, in communication systems, we tend to not talk about watts or milliwatts per se, but talk about them in terms of a logarithmic scales or a dB scale. And just give you an example of the two different types of measurements we may be talking about, we have system gain. So here is a block diagram here. We have a device under test, a DUT, power coming in, power coming out, and what is the gain? And we calculate that in dB as the ratio of the power out or the power in, the log base 10 and 10 times that. So if we want to look at, for example, a ratio of P out to Pn of 1, that's going to give us a 0 dB gain. Okay, there's no gain. If we have a ratio of 2, that is twice the power at the output, then that is in input, we have a gain of 3 dB, gain of 5, a ratio of 5 gives us a 7 dB gain. A ratio of 10 to the n will give us n times 10 dB. For example, if we have a gain of 10, 10 to the 1 gives a 10 dB gain. Gain of 100, that is 10 to the 2, gives us 20 dB gain. And a ratio of 1/2, that is if we have a device where half the power is lost in it, then we have a minus 3 dB loss. So gain turns out to be a positive number in dB, and loss is a negative number in dB. What about power? Well, if we noticed in the ratios or in gain, our units were dB. Well, when we're doing a power, we're really, we want to have watts floating around somewhere. Well, what we do is we take the ratio of whatever power we're considering relative to either 1 milliwatt or 1 watt. Okay, so if we're looking at a ratio relative to 1 milliwatt, which might be for very low power systems, we take our power, divide it by 1 milliwatt, and whatever that ratio is, take log base 10 of that and multiply by 10. If we have a higher power system, for example, a satellite that might be hundreds of watts, okay, we'll take the ratio of whatever that power is relative to 1 watt. log base 10 again and multiply by 10. So here's a couple examples of what we might have. A 1 milliwatt signal relative to 1 milliwatt in a dBm scale gives us 0 dBm. Okay, and relative to 1 watt, it's 1/1000th. A milliwatt is 1/1000th of a watt, and you take the log base 10 of that, multiply by 10, and you get minus 30 dBW. So between dBm and dBW, you're going to have a delta of 30 dB. 1 watt turns out to be 1,000 milliwatts, which gives us 30 dBm. But relative to 1 watt, 1 over 1 is 1 watt over 1 watt gives a ratio of 1. 10 log of 1, log base 10 of 1 is 0, gives us 0 dBW. And 20 milliwatts gives us 13 dBm and minus 17 dBW. Okay, so there's always 30 dB difference between dBm and dBW. So when we're talking about power, we need to make sure that we either have dBm or dBW. If we're talking about a ratio of powers, for example, a loss in a system or gain in a system, then the units are going to be dB, no M on it and no W on it. Okay, so let's start off our discussion of spectrum analyzers by, first of all, stating, well, what is a spectrum analyzer? Well, it's an instrument that provides a point-by-point, in terms of frequency, measurement of power. That is, as I look along the display on a spectrum analyzer, the x-axis is going to be frequency and the y-axis is going to be power. So I can look at how much power is at any particular frequency using a spectrum analyzer. Now this is in contrast to what we're more familiar with, perhaps, in terms of an oscilloscope. Okay, we look at an oscilloscope, we have our x-axis is time, and what we're plotting in the y-axis is voltage. So an oscilloscope does voltage versus time. A spectrum analyzer does power versus frequency. Okay, so if you go back to signals 171 or whatever class you may have had, this whole duality of signals lying in the time domain and the frequency domain. Oscilloscopes allows us to look at things in the time domain. Spectrum analyzers allows us to look at things in the frequency domain. Okay, well, how is the spectrum analyzer measurement accomplished? Well, the simple model is that we have a very narrow filter that we tune around the frequency that we're interested in. Everything else is rejected, and so only that frequency passes through, and then we go into a power detector. Okay, so a diode detector with a meter. Okay, so that's kind of the model. Well, the problem is this is not how it's implemented. Okay, and the reason is that not only is building a very narrow filter very difficult, okay, but making one that is tunable, that is has a unique center frequency, or one that we can adjust to look at different frequencies, is basically impossible. Okay, so so that's one part. The other part is that doing these point by point measurements of power for particular frequencies will be very tedious. So what we want to have, and what the spectrum analyzer does for us, is allows us to look over the power, look at the power values over a range of frequency. For example, if I'm interested into the power between 10 megahertz and 20 megahertz, then I could set up the spectrum analyzer to look at that particular region, and it will display the power of all the signal components in that range. Okay, well, how does it do that? Well, practical implementation is to use a super heterodyne front end. And this is basically the type of front end that you find in radio, in all receivers, okay, where you have a low-pass filter that sets up the upper range of signals that you may be interested in, and you're basically mixing your signal that's coming in with a local oscillator, okay? And the end result is when you multiply two cosines together, you get the sum and the difference, and you set up a intermediate frequency filter to pick out the component that you want, and the other one is rejected. Okay? So those who've had 174 have probably seen all this already, and those who are in 174 this semester, we will be getting to it in pretty short order, so not to worry. Okay, so a couple other things that we have that's of interest here is that at the front end, we note we have an attenuator here and an amplifier. Well, the reason why we have an attenuator here is so that we can basically pad down or knock down our signal so it doesn't overdrive this amplifier. As we know, practical amplifiers are only linear over a certain range. If I drive this thing too hard, it's going to be nonlinear. Nonlinearities introduce harmonics, etc., etc. Okay, so we have an attenuator we can set in the front end, and part of the lab experiment is going to show the effects of what happens if we don't use attenuation. Okay. Okay, so this particular design here allows us to create a practical spectrum analyzer, one that we can adjust the frequency of to look at particular signal components. Okay, we can set up a very narrow band filter, and we only have to design one of them, and this can be fixed at the intermediate frequency, or the IF. Okay, well, how do we get multiple frequencies? All right, like I was mentioning, we'd like to look at the power per frequency over a particular range. For example, the FM radio band. We might want to set up between 88 megahertz and 108 megahertz, and basically look at what the spectrum is, and look at all the signals in there and measure the power of each particular signal. Okay. Well, it sounds like what we need to do is basically sweep over a range of frequencies, and that's exactly how a spectrum analyzer is set up, and this is what we'll be dealing with in our lab. And the way it works is we utilize, or what's utilized in the device is called a VCO, a voltage controlled oscillator. That is, its output frequency is dependent on what voltage you give it. And what's inside there is a sawtooth waveform generator. So it's basically putting out a sawtooth shape as a function of time, okay, voltage versus time. As this voltage ramps up, the output of this VCO ramps up, and you're going to look at a higher frequency here. Okay, so you're going to be tuning your VCO, mixing it with a higher frequency, and looking at a different frequency component in your power detector. At the same time that you're ramping this voltage up, you're also ramping it across this display. So you're doing kind of an XY plot, where you're going to get the Y, which is the power, and an X, which is a function of the frequency. Okay, if this is varying linearly, this output's going to be varying linearly in frequency. So you're basically going to be able to plot the frequency that the VCO is at any particular time, and the power that you're measuring at that particular time. Okay, with some offset, but that's not really that important. Okay, so basically when you're looking at the spectrum analyzer, you're going to see it sweep across. You're going to see the display come across. All right, the power is going to go up and down as the signal components change in power as a function of frequency. You're going to skip back over to this edge, and then it's going to start over again, and that's going to correspond to this ramp going from the lowest left up here to the top, dropping back down again. Okay, when it's back down in here, you're starting another sweep. So this thing's going to be sweeping over and over and over and over and over again, and measuring power of the signal components. All right. So that's what you'll be able to see on the spectrum analyzer. Okay. So a couple other things that are interesting in spectrum analyzer design is that the amplifier in the power that's at the output of the power detector is a logarithmic amplifier. So it automatically converts the display into the dB scale. That is, you're going to be looking at, dBm. Okay, there's no mathematical conversion that's being done in the spectrum analyzer. It's actually done with a amplifier that has a logarithmic input-output curve characteristic. In addition, at the output of the power detector is a video filter, and the video filter is used to reduce the noise effects that the spectrum analyzer itself is producing. Okay, and so you can play around with this, the video bandwidth filter, or the VBW, to kind of clean up your picture. Okay, it turns out the spectrum analyzers we have, this is kind of a, I guess, a hidden feature. You really have to poke around on it. It's not as evident as it is on some units. But I guess the only downside is that you can use the video filter to a disadvantage. If you filter too much, you're going to really start distorting what your signal looks like, and it's erroneous. You're going to get erroneous output. So basically in all our experiments, we're going to kind of let the video filter be set automatically by the spectrum analyzer. But we should know that there is one there, and if you get into more advanced measurements, you may want to utilize an adjustment of that characteristic. But what we're really going to be concerned with in this experiment is what's the concept of frequency resolution. Okay, frequency resolution is the ability for the spectrum analyzer to separate two sinusoids into distinct responses. Okay, well, what do I mean by that? Well, let's say I have two frequencies. One's at 99 megahertz and one's at 100 megahertz. Okay, and I set up my spectrum analyzer to look at these two signals which are happening at the same time, and I would expect on my spectrum analyzer plot to see a spike at 99 megahertz and one at 100 megahertz. Okay, well, if I do, it means that, well, my resolution of the spectrum analyzer is at least as good as 1 megahertz, since these two things are 1 megahertz apart. Now, as I start bringing these two frequencies closer and closer together, you're going to find a point where you no longer see two peaks on the display. You're only going to see one peak. And what's happening, if we go back to our diagram here, okay, here's basically the transfer function of my spectrum analyzer. As these two frequencies lie within this particular bandwidth here, they look as one to this filter. The filter can't tell, well, is this, this frequency or this frequency, because they're both lying within the bandwidth. And it's just going to merge both the powers into one signal. So you're no longer going to be able to tell that there's two signals there. Okay, so frequency resolution is an important term that we're going to be dealing with throughout the semester. Okay, so the IF filter, as I just showed there, width determines the resolution bandwidth, the res bandwidth, or the RBW of the instrument. How far apart, and this basically tells us how far apart two signals need to be in frequency in order for them to be identified as two unique sources. Okay, and the width of the IF filter also determines the noise power in the system. Okay, the wider the filter is, the more noise is going to come in. So we're thinking, okay, well, if I make the filter narrower, it's going to let less noise in, so it's going to reduce my noise floor. That's a good thing. And if I make my filter narrow, I can also have two frequencies which are closer together and distinguish between the two of them, and that's also a good thing. So we would think, hey, let's just set the filter as narrow as possible. Well, the problem is that as you decrease the res bandwidth, okay, the longer the measurement will take. Okay, the longer the sweep time is going to be for your particular measurement. All right, and why is that? Well, it turns out a filter's response is inversely proportional to its bandwidth. Okay, so if you have a filter with very high bandwidth, it will respond very quickly. You have a filter that's very low bandwidth, it's going to respond very slowly. Okay, well, if I'm sweeping a signal through it, the signal is going to have to stay in there longer for it to respond. Okay, and bottom line is that the res bandwidth is going to determine the maximum sweep rate. And here's a nice little approximation that we're going to be using, is that the maximum sweep rate, that is how fast we can sweep our VCO, is going to be the res bandwidth squared divided by 2, and that's going to be in hertz per second. Right? So I can only sweep across the spectrum analyzer so many hertz per second determined by my res bandwidth. Okay, so let's look at an example of what we might have here. Okay, we have a signal that we're interested in, and we're going to set up the setter frequency, that is, what is the center point of the spectrum analyzer, to 10 megahertz, and we're going to set up a span of 2 megahertz. Okay, that is, I'm going to be looking at 2 megahertz chunk of the spectrum, and I'm going to be sweeping across it. Well, first of all, let's say if I set my res bandwidth to 100 hertz. That is, I want to be able to distinguish two frequencies that are within 100 hertz of each other, or as close as 100 hertz of each other. Well, using our maximum sweep rate calculation, That would be 100 squared divided by 2, telling me I can sweep as fast as 5 kilohertz per second. All right, well, how long is it going to take me to sweep across 2 megahertz? Well, that's my span divided by my sweep rate. 2 megahertz divided by 5 kilohertz per second gives us 400 seconds. Okay, that's a pretty long time, okay, to wait around for a single measurement. All right, so what we'd like to do is, well, let's increase the res bandwidth. Well, the downside of that is it's going to let in more noise, okay, in our measurement, and I will no longer be able to distinguish two signals that are, say, 110 hertz from each other. They're now going to have to be over 300 hertz from each other. Well, that may or may not be a problem depending on your signal. Okay. Well, how does that reduce my sweep rate? Or how does that reduce my sweep time by increasing the res bandwidth? Well, my sweep rate now increases ninefold to 45 kilohertz per second, okay, which allows me to sweep across the 2 megahertz in 44 seconds. Still a relatively long time. We're going to be finding that, we really, if we're sweeping across the screen at more than, it takes longer than a second or two, that's going to be a pretty slow measurement. It's going to be pretty fast, these things. So for this particular bandwidth, 2 megahertz, we're probably going to set up the res bandwidth to maybe 10 kilohertz. And as long as we're not trying to identify two signals that are very close together, then we'll be fine. Now we say, well, 10 kilohertz, that's a pretty big distance. Well, it is when we're talking about audio signals, okay? But when we're talking about radio frequency or RF signals, we're talking about signals that are spaced, megahertz apart. So, a res bandwidth of 10 kilohertz is, very, very fine relative to, the RF frequencies. So, a thing to kind of keep in mind is that, the type of signals that we're looking at versus type of signals that we may have looked at in 171, audio signals. We're not looking at audio signals anymore. We're looking at like radio signals. Okay, well, let's say, I just got, went on a bender and said, well, I want to be able to distinguish, look at 10 hertz resolution. Okay, now this is something that you may want to set up, for example, when doing audio signal processing. You'd like to be able to tell whether a signal was within 10 hertz of each other. Well, this is going to allow us a maximum sweep rate of only 50 hertz, and if I'm trying to sweep 2 megahertz, it's going to be an 11-hour measurement. So the bottom line is that when we are looking at very fine resolution, in the order of hertz, we need to do a couple things. One, either look at the very narrow band, okay, not 2 megahertz chunk, but something very small, or use an alternative method. And the main reason spectrum analyzers are not used for audio signals is basically because of this res bandwidth issue. So at low frequencies, what we tend to do is use a data acquisition card, a DAC, sample the data, collect it, perform a fast version of the discrete Fourier transform, the FFT, on our data, and then look at the spectrum. Okay, this is what we did last semester in 171. You may have done this in signal processing course or something like that. So if you're dealing with audio signals, you're going to be dealing more with the digital signal processing. We're dealing with RF signals, radio signals. We're going to be using a spectrum analyzer to accomplish the task. Okay, so this is kind of a summary of some background material. Here at the bottom of this page is some acronyms I use throughout. So when you print this out, you'll have that available. I guess I did use one other one, DUT for device under test. And we'll now step through the actual lab assignment. Okay, the objectives of this lab is basically learn how to use a spectrum analyzer. We have two different ones. We have a vector signal analyzer, this big HP box, which please do not try to pick it up, it's extremely heavy. And we have this portable spectrum analyzer, which is smaller than a laptop. So these two extremes of spectrum analyzers, and our goal is to try to see what each one of them will do. You have a pre-lab to do. I guess the key thing to keep in mind about the pre-lab is that I do want you to have a complete data sheet all ready to go for the lab. You should not be coming to the lab reading this procedure for the first time. Everything should be ready to go, and you should be able to knock out the lab in pretty short order. If you don't come prepared, then you're going to be in there a long time, and unfortunately, someone else may be bumping you off the equipment. So please come prepared. Um, okay, so here's a setup, basically how to get ready for all the components of the experiment. There's 5 parts. First thing is just playing around with some of the basic setups, setting basically the scale, kind of like you might do on a spectrum analyzer. Second thing to do is what happens when you start overdriving the input. Allows you to learn how and why you have an attenuator set up in the spectrum analyzer. The next couple, the next one, step 3, allows you to look at what happens in terms of res bandwidth when you don't have the res bandwidth set properly, or shows you that one spectrum analyzer is going to be good for measurements that the other one can't do. Part 4 is going to ask you to quantify how good the actual source is. Okay, we have a thing that's creating the signal and the spectrum analyzer is measuring it. Well, we can use the spectrum analyzer to actually look at the signal itself and say, okay, is this a good source or not? And we're going to see what happens when we start looking at 2 different power levels, when we really start pushing the spectrum at the source to its limit. And then finally, okay, some more we're going to look at in terms of the res bandwidth, another experiment there. And then finally, what happens when we don't really set up the spectrum analyzer properly? What are we going to see? It's basically going to, we're not going to be able to really tell much, but this is going to show you some nice things about what modulation is doing, and that'll be a key thing for the next lab. Okay, so in addition to your data sheet, which you should have filled out and turned in, you're to write a 2 to 3 page discussion, basically going through step by step what you did. And to help guide the discussion, I've given you some questions which you should be addressing. This does not mean only address these. That means that you should, at a minimum address these, but I do expect more out of it, and there's some more topics up here that you should address. Okay, this is it for lab 1. The lab assignment, these notes, and the Agilent tech note, application note are on WebCT.